And so we continue today in the second day of this conference, and I'm supposed to chair the sessions of today. So please don't hesitate of asking questions, or otherwise you will force me to ask stupid questions at the end if I'm not an expert in the talk. Questions, panelists can unmute themselves anytime they wish, but for attendees, they have to request this by raising hand, and they are welcome to do this, and we will unmute them. So for this first talk of today by Mikael Persson Sundqvist from Lund University, its title is The Ground State of the Pauli Operator. So go ahead, Mikael.
Okay, thank you very much for the introduction, and also thank you very much, Ayman and Wafa and Mikael, for the organization of this nice conference. I share with you a picture from another conference from 2017 when I visited Lebanon. It was very nice. So this the upper picture is Baalbek, so it's the temple of Jupiter, and the picture below is well, we had a lot of nice food, and this is actually from a dinner at Ayman's place. So I think Ayman's wife was cooking, and it was very good. Okay, so I will talk today about the ground state of the Pauli operator. That's a rather classical subject. I will share some experiences I have with this operator, and some of the things I will talk about are based on joint work with Ben Helfer and Hyne Kovarik, and some things are not. So here's a plan of the talk. I will first define the Pauli operator, so everybody will know what's the operator we are looking at, and then I will say something about the Arun of Cashier theorem. That's the classical theorem saying something about the kernel of the Pauli operator, the bottom of the spectrum. And then we will look at three different extensions. So first we will extend to more singular domains. I say singular magnetic fields it should be. So let's say fields. Then we should extend to higher dimensions, and then we should extend to domains. So the original theorem is for the full plane. So then we will look at domains. Okay. And I will write here. So let's start with the first one, and I will also say something about the Dirac and then the Pauli operator. So they are operators in the plane. They are describing spin 1/2 particles, charged particles. So the Dirac operator is the relativistic one, and the Pauli operator is the Hamiltonian, and it's non-relativistic. So just some notation. So we will write 4 points. I choose the somewhat strange notation, perhaps x1 and x2 like this. We will have a magnetic field. So a magnetic field. And that will be written as b of x, which will be a function bx1 and of x2, and then we write dx1, which dx2. So it's a 2 form, it's a closed 2 form, and we can identify it with this function capital B. So if you prefer, you could think about not being in the plane, but being in the space in R3 instead, and then you look at a particle that's confined to the plane, and then the magnetic field is orthogonal to this plane where this particle lives. I mean, that's a different view of this. And then we have also a magnetic vector potential. And what's this? This is a 1 form, which we will write like this. And this should satisfy something. Well, if we the magnetic field, it should be d of this 1 form. Okay, so this vector potential is not unique, as most of you know. We can add something and get new vector fields. We can add gradients of functions, so to say, more or less. Okay, but this means that b of x1 and x2, this is equal to dA2 dx1 minus dA1 dx2. Okay, so this is what we have. Then the Pauli operator is defined. It's a vector valued operator. So we look at vectors of functions with two components. And it's convenient to introduce the Pauli matrices. So these are three matrices, which is 1, 0, 1, minus 1. You can choose them a bit differently if you want. 0, 1, 1, 0. They are Hermitian. So 0 minus I, and 0. For example, you can choose them like this. And then these matrices, they satisfy some relation, so some Clifford algebra relation. Which says that if you take sigma j, sigma k plus sigma k, sigma j, this will be 2 times, and then delta jk, which is of course 1 if j is equal to k and 0 otherwise, times the identity matrix. Okay. We also introduce magnetic momentum operators. And we denote them by pi, capital pi, pi j, which is minus I d dxj minus aj. So that's the sign convention we use here. And then we can describe the Dirac operator d, which is just the sum sigma j times pi j, and j goes from 1 to 2, so it's just the sum over the first two ones. And then the Pauli operator, it's the squared of the Dirac operator. Okay, so these are operators in, so we work in L2 of the full space, but we have vector valued functions. So something like this. This is the Hilbert space. And then if we take, so if this is the Hilbert space, if we write elements in this Hilbert space as U plus and U minus, then we call them spinors. And U plus is then the spin up component, and U minus is the spin down component. So let me not say that. Okay, so this is the Pauli operator. I don't say so much about the domain here. You can, for example, if the magnetic field is sufficiently nice, then we can just define it by the quadratic form and the Friedrich extension, for example. We go to the statement about the ground state of this one, the Arun of Cashier theorem, and this is from 1979. Okay, so since the Pauli operator is the squared of the Dirac operator, it's non-negative, and so the bottom of the spectrum, it could be 0, and actually it is 0. So if we assume that B, the magnetic field, say that for simplicity we take something that has compact support and is C1. This can be weakened, and it has been weakened, and we will soon discuss much more singular magnetic fields. and then we let phi, capital Phi, that denotes the flux of this magnetic field. So we integrate over R2, and then we integrate B, so say B of x1, x2, dx1, dx2. So it's just the integral of this magnetic field, that's a number. Then the dimension of the kernel, the dimension of the kernel of the Pauli operator equals some function here of absolute value of phi, and this function is essentially some integer part. So if we this one is the what should we say, it's the biggest integer, strictly biggest integer, strictly less than s, if s is greater than or equal to 1 and 0 otherwise. Okay. So the important thing here is that the dimension of the kernel is, well, it depends on the flux, of course, but it's usually greater than 0. So we have something sitting in the kernel, and that's the Arun Cashier theorem. So that says, it says something then about the bottom of the spectrum of this Pauli operator. Okay, so since we will need some notation, I will just say something about the proof, because we will use notations from this later. So sketch of proof, and so this is very classical. So one introduce creation and annihilation operators, and let's call them Q, which then is equal to pi 1 minus I pi 2, and we write the star, it's the other one, then it's pi 1 plus I pi 2. And then, as a matter of fact, one can write the Pauli operator as well, it's 0 q star q 0 squared, because that's the Dirac operator I have written there, and then this can be written as q star q 0 0 q q star. So the Pauli operator is really a diagonal operator. As we will see later, this Q star Q is the Schrödinger operator with the same magnetic field plus or minus B. So we really have a diagonal operator with the Schrödinger operator on the diagonal, and then plus minus the magnetic field B. That will be something we see later. So what does this mean? This means that if we have something in the kernel here, Q of this should be equal to 0. Q of U plus should be 0, and Q star of U minus should be 0. So U, which is U plus U minus, it belongs to the kernel of P precisely when so let's see, so Q U plus equals to 0 and Q star U minus equals to 0. Okay, so as I said before, we will need some notation from this as well, and it turns out that it's useful here to use complex analysis instead of real looking at R2. So we identify the point x1 x2 with x1 plus I x2. look at this in a complex setting. And then we introduce also the scalar potential. So the scalar potential here, it's a function psi satisfying that the Laplacian of psi is equal to b. That's the convention we use here. So this is of course not unique either, but we will see later that there will be good choices. And then, as a matter of fact, it's a calculation that says that q of u plus is then equal to minus 2i e to the minus psi d dz bar e to the psi, and q star of u minus is something similar. It's minus 2i e to the psi, and then we differentiate with respect to c instead of c bar, and then it's e to the minus psi. Okay, so we can see where this is going, because now the condition to be in the kernel of the Pauli operator, that will be a condition that a certain function will be holomorphic or anti-holomorphic. I forgot to write u plus and u minus there. So from the conditions above, so we must have, what do we need? Well, ddc bar of e to the psi u plus should be 0, and ddc of e to the minus psi u minus should also be 0. Okay, so I will almost I'm almost finished with this. So we choose psi as well, essentially you take 1 over 2 pi, you take the logarithm, and then you convolve it with b. So that's a scalar potential. In this case, we have the fundamental solution. So with the sign choice, I hope I wrote this correctly. And with that one, we have that this is more or less minus the flux times the logarithm of absolute value. So with a small error. And then we'll see that when we take e to this psi or e to this minus psi, it behaves as absolute value of z to absolute value of z to minus or plus capital phi 1 plus 1. So this is when z tends to infinity. And then we can see that we should have entire functions or anti-entire functions, and they should behave, and we have the certain asymptotics, and that will force, depending on the sign of phi, this will force one of the components to just be the zero function and the other one to be a polynomial of the right degree. So yes, I write apply Liouville type argument. So that's the end of it. So we have, I mean, what we should remember now is that this creation and annihilation operators are used in a good way to describe this Pauli operator. So instead of using what's more, I mean, commonly used for Schrödinger operators, those momentum operators, which are expressed in terms of the magnetic vector potential, we use these creation and annihilation operators, and we write them in terms of complex derivatives, and then we can use this scalar potential instead. Okay, so that's one of the points. Leo will, there should be an E there as well. Okay, so the conditions, I mean, this theorem is, as I say, classic, and the condition on B has been relaxed a lot. So I mean, for this operator to be well defined, as I have written it, one usually assumes that this vector potential should be locally in L2. But people have also been able to extend it further, and that's the next point, which is the first extension. And I write Arun of Bohm fields. Okay, so the first extension, what happens if we try, I mean, is it even possible to define this Pauli operator in case of very singular magnetic fields? So we will look at, and I use now the complex C here instead of X. So we will use B, the magnetic field will, sorry, it will be some nice field plus, say, some sum of Arun of Bohm magnetic fields, which we write like this. So we add the delta distribution as a magnetic field, so it gets very singular, and we do this with the fluxes alpha j. So we will see later that it's, or I will tell you later that it's possible to reduce it so that one can assume that alpha j belongs to the interval 0 to 1, for example. But yeah, let's come to that. So we assume that this one is still a nice, well, let's write it with C now. So this one is a nice field, and we denote the points where we have put this singular magnetic field. We denote it by capital lambda for a while. Okay, so if one wants to find a magnetic vector potential corresponding to this, well, corresponding to the smooth part, it's not a problem. So we get some A naught, which is a smooth function, and then we get a sum. I mean, this is one of the choices, a sum alpha j, and then we divide by x minus xj, if I'm allowed to write it like this, and we take that squared, and then we take minus x2 minus x2j. So these are the second components of the jth points. So that's why I write those 1 and 2 upstairs and not downstairs. And then it's x1 minus x1j as well. So it's a sum of terms like this. And as you can see, they are a bit singular when x is equal to xj. So this means that the quadratic form which corresponds to the Pauli operator, which is this one, so it's sigma j pi j u squared dx. This one is not well defined. On say C0 infinity of R2, C2. Because simply, I mean, this A, the magnetic vector potential is too singular, so you can find, take a function which is essentially constant in the neighborhood of such a singular point, and you will get something, you will get that this integral is divergent. Okay, but on the other hand, if one uses that for smooth fields or regular fields, let me write smooth fields, then one can write this quadratic form. Instead of using these magnetic momentum operators, one uses the creation and annihilation operators, and you write it like this, integral over R2. So Q of U plus squared plus Q star of U minus squared dx. And as it turns out, this one is possible to define. Which can be defined on C0 infinity of R2 at least if these fluxes are between -1 and 1. So you can view these derivatives, these complex derivatives that are building up this Q and Q star. You can view these derivatives in the sense of distributions, and if you do so and write this down, you will see that if you take alpha j's, which are between -1 and 1, this is well defined. So this is work by Erdős and Vogalter, and it's from 2002. So doing so, you can define this quadratic form, and you can define a self-adjoint operator from this. So I write it PEV, and so define from this. Okay, so you get one Pauli operator defined with this singular magnetic field, but as I somehow indicate, there are more of them, and as many of you know, when you have Aronoff-Bohm magnetic fields, the operator defined as you usually define where you take away the point and so on, it's not essentially self-adjoint, but you have several self-adjoint extensions. But this is one of them.
Excuse me.
Yes.
When you say one is well defined and the other not, but in fact they're the same thing, right? So you mean
no. They are the same for regular magnetic vector potentials A, but I mean this Q and Q star, they are built up with a scalar potential instead, and then it's possible to make sense even of this, even if you take the singular fields actually.
Okay, thank you.
So this is discussed in this Erdős and Vogalter paper.
All right.
Okay, and it's also so they. Okay, so you don't want to have this condition that alpha j should be between -1 and 1. So what they do is that they define the operator via gauge transforms if you happen to be outside the interval of -1/2 and 1/2. And then you get something. And what they are also able to prove is that the dimension of the kernel of this, it happens to be the same thing. So, and I mean the proof is almost the same. So you will actually get functions which are analytic, and yeah, so it works the same way. So if you instead starting with C0 infinity, and then you take R2, but you take away those singular points. Then you can define another quadratic form, and then this, if you look at the derivatives in terms of distributions on this set instead, they will not really fill those Aronoff-Bohm fluxes, and you can define a Pauli operator, which so it gives a Pauli operator, which I would call, say, the maximal Pauli operator. So you just add as many functions as possible. That still makes this the quadratic form finite. Okay, and this is something I looked at, and by that time I was called Persson only. So so then we get something different here. So the dimension of the kernel in this case is equal to, well, it's equal to this raise function of phi plus n minus phi. Okay. So the reason that we get something different here is that we allow now that functions actually might have some poles depending on the flux and so on. So at those points you might have poles, simple poles as well, and then you count. So you get, once you take away that part, you will have a polynomial, and then this is what you end up with. So depending on signs and so on, one of these terms will come from the Q and the other from the Q star. Okay.
Sorry, Mikael.
Yes.
So just to let you know that the photo is still appearing all the time.
It's still appearing, yes. Isn't it nice?
Okay. Nice for me, I mean, but it's up to you.
Okay, so maybe it's better if I try to follow the pages like this. Thank you, Ayman. Okay, so I will tell you one more family of operator, one more way to look at these singular fields. So one could start with.
Michael,
sorry, I don't hear you well, but I think you wanted to say something.
Yeah, I wanted to ask who is little n? I just forgot who was little n.
The little n was the number of Aronoff-Bohm fluxes, so to say. So the number of points.
Okay. Sorry. Right.
No, that's
so
fine.
it doesn't depend on alpha then. It's not the intense.
No, so alpha. I mean, it in some sense it depends on alpha because when you integrate, you get fluxes. I mean, so phi is depending on alpha, right?
Okay, and you still have the condition that alpha be between -1 and 1 for this.
Well, to define the operator, you don't need that anymore, but you get gauge invariant, so you can assume, and here we have assumed that alpha is between 0 and 1. So
okay.
Yes.
Okay, yeah, thanks.
And sorry, related question. So this P max was a particular self-adjoint extension that you showed?
Yes, exactly, and that's what we get when we start with this smooth functions where we actually remove the singular points. So we look at the distributional derivatives where we have removed the singular points, so they are not felt anymore, and then we can add, so to say, more functions than it was possible for Erdős and Buchalter, because they were still
the closure sort of this.
Yeah, exactly. So you take the form and you add everything that all the functions in L2 such this form is finite. I mean the maximal version, and then you get the self-adjoint extension from that, right?
Thanks.
Okay. So another way to start with this would be to take the Dirac operator. So remember, so start with Dirac. So I will not say too much about this, but so then the Dirac operator is a first order differential operator. It's possible to look at if you only have one Aronoff-Bohm solenoid, then you will have a symmetric operator with efficiency index 1, 1, and then you get the parameter of extensions, and then you can patch together if you have several ones, and you get a family. So you get a family, say p tau, which is d tau squared, where tau is some parameter, which is taken in this interval 0 to 2 pi. Okay. And then you get the dimension of the kernel of this p tau. It equals, well, that can be different for different values of psi. So it can be anything from absolute value of n minus phi, and this curly bracket. It can be this one, and it can be 0 depending on tau. And actually I can write tau equal to 0, tau equal to pi, and otherwise here. But it doesn't help you so much if you don't know what tau is. But it's one of this. It's a way to parameterize those self-adjoint extensions of the.
So what is d tau? What is d tau?
D tau is a self-adjoint extensions of that. So it's the Dirac operator. So you start to define the Dirac operator. You define it first on nice functions, and then you see that. I mean, you can really do these calculations of deficiency indices. You will get deficiency index 1, 1, and then you can parameterize all the self-adjoint extensions. Say if you started with one Aronoff-Bohm solenoid, and then if you have this magnetic field that we have, then you can just patch it together and get a self-adjoint extension.
Mm.
So it's a Dirac, yeah. So when you solve this deficiency, I mean, you will get some Bessel functions in the, and that will give you some asymptotic. So it will tell you how these functions in the domain are looking close to these singular points. Okay. So that's the Pauli operator with singular magnetic field, and we move on.
Sorry, may I ask a quick question? So the Pmax before is in the family, I guess. Or...
No, it's actually not in that
okay.
family. So Pmax is not a square of a Dirac operator. So that's something we discuss as well.
Okay.
So this is from 2006. So this family. So it's not. So we discussed these properties, the being a square of a Dirac operator, and also you should somehow have some symmetry between the spin up and spin down component when you switch the sign of the magnetic field and so on. And it's there are other properties to look at. Okay. So higher dimensions. So maybe I should be quick here. How much time? I have 10 minutes left, and I have two more points to say. So let me just be very quick here to say that you can use complex analysis. So we are now in CD, say. So we have 2D real variables, or D complex variables. You can use complex analysis, and you can define, so to say, weighted D bar operators. So let me just write something down. So this is then e to the minus say psi, d bar, and e to the psi, and we define this on forms now, on complex differential forms, and we look at 0Q forms, so 0, 0, 0, 1, 0, 2, 0 up to 0D, so sums of such forms, and we can define it like this. So this goes back to Shigekawa. think, from 91. And then we can define the Dirac operator. So the Dirac operator will be 2 times such a psi d bar psi plus d bar psi star. And then Pauli is the square of the Dirac operator. And then it's possible to use complex analysis tools to say something about the kernels here as well. So for example, Shigeakawa proves that if you take, well, what should I say? So if you take the magnetic field here, B, it's now a 1-1 form. So it's not a general 2 form. So B is some sum of BJK, dz. What should I write? dz wedge dz k bar. So if you look at the matrix BJK, mu of z is the smallest. Well, it's the absolute value of the smallest. Let me see, what do I want? I want the eigenvalue of BJK, and the smallest one, smallest absolute value. Then if this mu of c times z squared, so if this goes to plus infinity, so if this eigenvalue grows, so that's a 2, if this grows quicker, faster than 1 over c squared, then the dimension of the kernel of this Pauli operator is infinite. So you have infinitely many such things, and they usually sit in the lowest form or in the highest form, because that's where you can do something. Okay, so I was perhaps missing a bit with the time here, but let me not say anything. So I will say, I can say if these eigenvalues behaves, if they are just like going like 1 over absolute value z squared, that's a difficult part, and that's where you can have some flux condition as well. So let me not go into details there, but go on to the next one, which is domains in the plane. And this is the most recent work, which was done with Bernard Elfer and Hynek Komarek. So then omega. So now we are back in the plane. Omega is the domain here, and we cannot really say, if you just have a domain, it's difficult to say anything about the kernel of the Pauli operator, but perhaps if we look at the semi-classical operator instead, maybe we can say something. So then it turns out that we can write it like this, minus IH dx1 minus A1 squared plus minus IH d2 minus A2 squared, like this. And then we have plus or minus HB. So if you write out what the Pauli operator is, it's really this diagonal operator with these two components. So you get the usual Schrödinger operator plus minus H times B. And then what can we prove? So assume, well, we have different, it's actually a series of 3 papers, but I state some rather maybe the first of these results. So assume that omega is simply connected. And we assume that B of x is positive in omega. So we have magnetic field with a sign. And we assume that psi is a scalar potential, which is 0 on the boundary. Okay, so this we assume. Then if we take the bottom of the spectrum of this, say P minus here, that will be the smaller one of these two, because we take minus a positive term. So if we take the bottom of the spectrum of that one, it will depend on H and B and perhaps also omega. And then we multiply this by, well, we take the logarithm of it, and then we multiply it by H. And then we take the limit as H tends to 0. Then this will be equal to 2 times the infimum in omega of this psi, this scalar potential psi. Okay, so this is something that we actually can say. So what does this say more or less about the this eigenvalue? So this is the bottom of the spectrum. What does it say about this? It says that it is exponentially small. So this says that this lambda p1 is exponential small, and it also makes it precise in terms of this scalar potential psi, which is.
Mikael, is there
I
a
have
boundary
written something.
condition?
Sorry, once more.
Is there a boundary condition on your operator?
It's a Dirichlet one. Yes. Thank you. So it's the Dirichlet Pauli operator that we look at. Okay, so it will be exponentially small. So how do you prove something like this? Well, what you do, what you really want to do, is that you want to use this complex analysis way of writing things. That's why I started with that. You really want to use this, write this with this form with the creation and annihilation operators, and then you start to do the estimate, so to say. So the lower bound is explicit and it's not semi-classical. So the lower bound is actually something like this. So that it's not semi-classical, it's h squared. It's the lower bound of the Dirichlet Laplacian in omega, and then it's times exponential, and then it's 2, and then it's psi min, which is this thing, psi min divided by h. So that's something that you just write the quadratic form, and you do some clever rewriting with this complex terms, and this is what you get. So this is the bottom of the spectrum of the Laplacian. Dirichlet Laplacian in omega. Okay. Then there are, well, yeah. So I think my time is almost up, so I will not. I think I better stop here and then answer if there are, try to answer if there are questions. So the upper bound is semi-classical here, then we're not able to prove something like this. And I should say that this is inspired by work of Ekholm, Kovarik, and Portman as well. So it was when we read their work that we started to look at this, the Pauli operator here in the domain. Okay, so you have seen some flavors of the bottom of the spectrum of the Pauli operator, and I let it be here. Thank you very much.
Thank you very much, Mikael. So now we still have some time for questions, please.
Can I ask one?
Yeah, of course, Douglas.
Thanks a lot. And so first, do you have some conjecture concerning other boundary conditions in this?
No, well, for the Neumann condition, I don't remember, but I remember that Bernard told me that no, we will not get something similar there, but I don't know what you get actually.
And also, so there's this, probably you're aware that there's a relationship also to the models that I discussed. I don't know if you recall, or if you follow the talk, but there was these anion operators.
Yes.
Essentially Aharonov-Bohm, but it's not the Pauli operator, but you can think of somehow adding, or you can look at adding or subtracting some potential which matches this thing. And so in the anion problem, there's also essentially two ways to regularize this thing. So one I mentioned that you can sort of make this similarity transformation by sort of putting in essentially a function of the distance or something like this. And the other way is to sort of smear out the flux. So I was just curious whether you considered any of these regularization procedures in your work.
No, we didn't regularize at all to look at that. No, we didn't. I know. I mean, I know that people have looked at some resolvent, say, convergence of regularized operators in these settings, but we didn't use this at all here. No.
Thanks.
Well, thank you, Douglas.
Yes.
There is a question by Bernard.
Another question. I wanted to know whether those eigenfunctions, those functions in the kernel space, they survive somehow in the domain. Do they have a?
Sorry, I'm not able to hear very well.
Yes, I wondered whether the functions in the kernel on the whole space they play a role somehow in the domain problem, or do they appear somewhere?
No, well, not really that they appear, but I mean we are a bit inspired of that situation when we construct the trial states somehow. But in the end, we write down a trial state that actually satisfies the Dirichlet condition. So no, so we do not really see. I mean this.
In fact, that was exactly what I meant about.
So the trial state we write is the following. I just write it down here. So it's exponential of minus psi divided by h. And then it's minus exponential of psi divided by h. So thanks. I mean, we know that this psi is 0 on the boundary, so this u will actually be 0 on the boundary as well. And it just turns out that this trial state works very, very well. And yeah, so.
May I ask if you have any results on the semi-classical estimates of spectrum for Dirac operator on bounded domain?
No, we haven't looked at that.
Okay.
And I don't know exactly what they should say either, since well, I don't know much about the spectrum of the Dirac operator. I mean, we don't have this semi-bounded operator anymore, and I don't know how it should look like.
Mm-hmm.
But maybe that's interesting to look at.
Okay, so we go for Bernard's question as well. So apparently there are many questions.
Oh, good.
So Bernard, then
I just
okay.
Can I speak? Hello?
Yes, yes, Bernard. Yes, yes, you can speak.
Just a comment about the question about the boundary condition. So if you take the constant magnetic field and the Neumann condition, you are exactly in the situation up to some translation by plus or minus HB. You are exactly in the situation which is considered in surface superconductivity. And so you can apply all the analysis which is done for the Schrödinger operator. But we know that the situation is completely different. Okay, that's all.
Yeah,
Okay.
Thank you, Bernard.
Thank you, Bernard. So Jakob has something
Yes,
to
may
say.
I ask just, did I understand correctly that the domain is always simply connected in
Yeah,
all
well,
these results?
no, well, in the first paper it is, but then we extend the results, but then it becomes a bit complicated because there might be fluxes from when you walk around.
Exactly, if you just consider, for instance, the annulus with a flux in the middle.
Yes, indeed, and that's a bit difficult to handle. But I mean, we get some similar semi-classical results, but in the end, in fact, I think the most problematic part for us was to understand this scalar potential function, how it looks and how it works.
Okay.
Because it can be a bit. Yeah, and I mean, I suggest that you go and look perhaps in the first of the three papers, because there is discussed this problem of properties of this function. If you, I mean, it's a problem that's not only discussed in the connection with magnetic fields and so on. If you take the Laplace, I mean, this Dirichlet, the Poisson problem, and then so it gets more complicated, certainly, but we can say something at least.
Okay.
Okay, thank you very much. So maybe there is room for one question by Horia, because he was raising hand. So maybe we take this last question before we go to the other talk.
Okay, thank
Horia, you hear me?
Yes.
Okay.
So I have a question related to the first part of your talk, the one with the Cashier theorem. If you have the constant magnetic field, then of course the result is kind of the same, no? Because you have infinitely many.
Yes, indeed.
Okay. Yeah, but what happens if you have a periodic magnetic field? So you perturb a constant magnetic field with something which is periodic but much smaller. So in principle, you know that this operator will still have gaps.
I don't know, but I mean, but my guess would be that if the flux is infinite, then you will have an infinite kernel. I think that's true.
So at zero, you say that you still have an eigenvalue which is embedded in the spectrum. That's what you think.
Yeah, well, yes, that's what I would guess, at least. Well, I know. I mean, that's my guess, but it's just a guess. What do you think?
It would be nice to be able to prove it. I don't know.
Yeah, so maybe one can look at some. Yeah, I don't know. Maybe it's possible to do. Maybe something has been done that I haven't been.
And Bernard must have done it.
Yeah.
Thank you very much, Mikael, for the nice talk. And we apologize for not accepting questions because time is up. So we